Equivalent circuit of a synchronous generator. So a synchronous generator has a field winding and an armature winding. So when we will be developing a complete equivalent circuit, we will work with both of them. Field winding is supplied from a DC supply, so that's why you have winding represented by a resistance and an inductance, and that's going to be supplied from a DC supply. So here is the DC voltage. Let's keep it VF, so that shows the field winding parameters. This is the resistance, so we're gonna say RF, that's the resistance of the field winding, and this is the inductance of the field winding again. Now in order to control the current flowing through it, because we know the EMF or the voltage induced in the armature or the stator winding depends on the magnetic field produced by the current flowing through the field winding. So in order to control that EMF induced or the generated produced voltage, we will be changing the field, and in order to change the field, the magnetic flux, we must be able to change this current IF. So in order to change that, we will insert an external resistance in here. Let's say, I'm gonna say here is that resistance, and I'm gonna say this is resistance R, adjustable value, and I'm gonna say it's a variable as well. So this arrow shows that this value can be 0 or it can be any non-zero value as well. So it's a variable resistor, and it's an externally added resistor to control the current in the field winding. So that's the field winding. Now we have armature winding. Armature winding, what we have is, from armature winding, voltage is produced, and we also know that it's AC, and we know that it's three-phase. So you will see a three-phase winding in here, and the three-phase winding can be either in Y or in delta. So in order to see the complete circuit for the armature winding, this is how it's going to look like for complete three-phase. Okay, so that's the armature winding or the stator winding in the three phases. So phase A, you can say phase B, phase B, let's say, and phase C. So this is the Y connector synchronous generator, the armature winding, and that's the delta connector. One thing which you notice in each case, so each phase of the winding is represented by a resistance, an inductance, and then the induced voltage in each phase. So under balanced conditions, each phase present the same circuit as the every other phase. So with respect to looking at the equivalent circuit, what we do for synchronous generators for the armature side or for the stator winding, we use per phase equivalent circuit to do the analysis, and then we say the same thing applies to other phases. So in case of per phase equivalent circuit, we only use one phase, one line, and the other as the return path, and it could be true for a delta or for a Y, because that does not matter in case of per phase. It's only a single phase quantity in case of per phase. When we look at differentiating delta or Y connection, we'll be looking at how the phase and the line quantities are related in terms of voltage and the current variables. So based on the discussions we have for three-phase systems, in case of Y connection, I line equals to I phase, and VL equals to √3 times V phase. And in case of delta connection, the phase and the line voltages are the same, but the line current and the phase current are related to each other through a factor of √3. So let's use per phase equivalent circuit for the armature or the stator winding of the synchronous generator, and the complete equivalent circuit looks like this. Okay, so that is the per phase equivalent circuit for the armature winding of the synchronous generator. Here you have the internally generated voltage. It's called internally generated voltage. That's the armature winding resistance. That's the armature winding reactance, XS, corresponding to the inductance. And in case of synchronous generators, it is called synchronous reactance instead of armature winding reactance. Synchronous reactance. Okay, and here at these two terminals in here, this voltage is called armature terminal voltage. So we need to distinguish. This is armature voltage as well. That's armature voltage too. We call this armature terminal voltage, and we call this as a armature internally generated voltage. So terminal voltage. And the quantity, last quantity here is IA. That's the armature current, and make sure that you pay attention to the direction of the current. It is going from the machine to the outside connection, so that's why it is going into the terminals, which is going to be connected to the outside. So under no load conditions, you know that there is nothing connected to the terminals of the generator. So under no load conditions, you're going to have IA equals to 0, no current drawn from the generator. In that case, EA will be equals to V phase. As you can see, once IA is 0, there's not going to be any drop in here, which is keeping this point different than that, since the drop across between these 2 points is 0. So this point and this point are at the exact same potential. That's why V phase equals to I phase, EA under no load conditions. Now when generator is loaded, in that case for a loaded condition, depending upon the amount of the load, IA of course is going to be non-zero, and EA will not be equals to V phase either. Now what is the exact relationship between V phase and EA in that case is? What we're going to do is we're going to apply KVL to this circuit. So I'm going to draw this circuit one more time, and I'm going to apply KVL to write the equation to relate the voltages, the two voltages, the terminal voltage and the internally generated voltage. Okay, so apply KVL to this one loop. It's a series circuit, so apply KVL. We go clockwise, and you can start from any component. Let's say I'm starting from EA, so it's negative EA as I'm approaching the negative end first. Based on the direction of this current, so the drop across the two components in here is going to be plus and a minus, plus and a minus. So in that case, the next term is a plus, and it's a IA times RA. The next term is also positive, and the next term is IAXS, and the last term here is positive to negative, so positive V phase equal to 0. And based on this, I can write that V phase equals to EA minus IARA minus IAXS, or it can be EA, you can take IA common, RA plus IXS, where IA is the armature current, EA is the internally generated voltage in the synchronous generator, V phase is the terminal voltage, but this is a single phase equation, keep in mind. Armature winding resistance and armature winding reactance. Now we'll be looking at the impact of power factor loads, different power factor loads. So we're looking at impact of unity, lagging, and leading power factor loads. Now, in case of unity power factor, the terminal quantities, which is V phase and IA, are going to be in phase. So we're going to start with the V phase as our base phasor. So V phase is at 0 degrees. And in this case, you have current exactly in phase with it. So here is going to be IA. So what we have is, we have V phase. The equation was V phase equals to EA minus IARA minus I, that's a 90 degrees angle, IA axis, or you can write this equation as EA equals to V phase plus IARA plus IA axis. So let's say in order to implement this equation, we have the first phasor, which is V phase, then we're going to add IARA to it. So IARA is going to be a phasor which is going to be exactly in phase with I phasor. Because RA do not contribute any angle. So after, we're going to start from the end of V phase. So here is going to be the phasor IARA. Then the next added term is IA axis. So again, IA has its own angle. Axis contribute an angle of 90 degrees as it is shown through this I. So that means this phasor, this term IA axis, will be at 90 degrees to IA. So IAXS has a positive angle of 90, so this will be leading IA by 90 degrees. Since IA phasor is here, so IA axis is gonna start from this end of IARA because it's added to that, and then it will be at 90 degrees to IA's position. Okay, so now we have V phase and then IARA and then IA axis all added together will give us the resultant phasor, which is EA. So that's the phasor diagram for a unity power factor load. And this angle, the angle between V phase and I phase, is defined as delta, and its name as internal angle, torque angle, power angle. Few different names are given to it. So it's called internal angle, torque angle, and I believe power angle is another name for it. Okay, so that's the impact of the case of a unity power factor. Now let's see what happens in case of a lagging power factor. So for lagging power factor, IA lags behind V phase by any angle, let's say theta. So we're gonna start again from V phase. That's the base phasor V phase, and here will be IA lagging behind V phase by an angle of theta. So that means IARA will be in phase with IA. So here will be IARA, and IA axis is at 90 degrees to IA. So that is how it's going to be 90 degrees to IARA as well. So IA axis, and the resultant again is E in here. And again, this is the angle delta, and that's it. And now let's see the case of leading power factors so that we can compare, we can make a final statement. In case of a leading power factor, we have IA leading V phase by, again, let's say theta. So this is a case of lagging power factor. So here is your V phase, and I is going to be leading, so I is here again by an angle theta. So that is how IARA will be in phase with the IA, and XS IA axis will be at 90 degrees to that, so this angle is 90 IA axis, and the resultant is again EA, and this is angle delta again. So when you compare the two cases, and even the case of a unity power factor, so for any given phase voltage V phase and the armature current IA, a larger internal voltage, which is this in here, larger internal voltage EA, is required for lagging loads than for leading loads. So let's write down this statement. So for a given value of V phase and IA, for a given V phase and IA, larger EA, which is internally generated voltage, is required. So a large generated voltage is required from the generator for feeding lagging power factor loads in comparison to leading power factor loads. Okay, so now we have induced a current in the armature as IA, and this current in the armature also will induce the magnetic field called stator flux, or the stator magnetic field. And let's say if we want to say exactly in terms of flux density, so we call stator flux density. So the induced armature current IA induces a stator flux density, let's say is called BS. S is for stator. Now this is going to be superimposed on the flux density from which is produced from the field winding, which is rotating, is called from the rotor. So which was, let's say, represented by BR. So that's the flux density from the rotor. So both of them are superimposed. And in that case, the net flux or the net field is going to be the sum of BR and BS. So in here, let's clarify. So BR is what that generates EA, the voltage. At the same time, the B net is what generates the phase voltage, the terminal voltage, V phase. And then there's an angle delta between between V phase and EA. It's the EA. It's the same angle which is between BR, because BR is generating EA, and B net. Now let's look at the torque or the power in case of a synchronous generator. We looked at the generated voltage so far. Let's look at how does the power and torque in a synchronous generator work. Right, so let's consider the power and torque in a synchronous generator, and we're taking the case of lagging power factor load, and in this case we're assuming that RA is approximately equals to 0. That's why we're considering that IARA equals to 0. And what does the synchronous generator does? It converts the mechanical power into three-phase electrical power. So in case of, if we are just writing single phase equation, let's say we're saying it's the apparent power, I'm writing the equation for, and the single phase for one phase only, it's going to be the product of the voltage and the current, so V phase IA. And in case of three phases, so we're gonna just change it to 3 times one phase. So S output in case of three phase is going to be 3 V phase IA. And if we are looking at the active power or the real power P, again in three phase, so that's gonna use a power factor with it, 3 V phase IA cos theta. And if we are looking at the reactive power Q, that's going to be 3 V phase IA and sine of the angle theta. So in case of three phase. Now let's look at what else V output can be expressed as in terms of the internally generated voltage. So let's look at the this phasor diagram. This component in here, the vertical component, this component, okay? Let's say I'm looking at it in terms of the phasor EA, which has an angle delta with respect to the so for that we have this height. This height is given by EA sine of delta, because it's a perpendicular distance for that. At the same time, if we look with respect to this triangle, which has a diagonal distance of IAXS, and we should be aware that since this angle is theta, which is between IA and V phase, now you have IAXS at 90 degrees to that, and you have this vertical line at 90 degrees to the horizontal V phase line, so that's how this angle is theta as well. And if that angle is theta, so this is the base of the triangle which is making use of IAXS. So this distance is also IAXS cos theta. So in the equation in here in P out, what we're going to do is, so we have IA cos theta. We're going to replace that with EA sine delta divided by XS. So that means P output is going to be 3V phase. So what I said, IA cos theta is EA sine delta divided by XS. And delta is again internal angle, torque angle, and that's the angle between V phase and EA. Delta is also the angle between BR and B net. So again the equation becomes 3 V phase EA over XS sine of delta. So that's the expression for the output power from a synchronous generator. And let's see what it is for torque. So for torque, we're aware that, let's say we're talking about induced torque, produced torque is given by the power divided by the speed the machine is running at. So if we make use of that, and that's applicable for any machine, and if we apply it to synchronous generator, the power equation, the real power equation was that, so it's gonna just divide it by the speed the machine is running at. So that's the expression for the torque. At the same time, we can express torque by using magnetic fields as well as the cross product of the magnetic fields, or it's K BR B net. Again, here delta is the angle between BR and B net, so that's why it gives us BR B net sine of delta as the torque induced in case of synchronous alternator. So this is true as well. So delta is the angle between BR and B net. Okay, so that's about the synchronous alternator, and now we're going to discuss an example on it. Okay, so here's the graph of 532. So that's 500, that's 550. So 532 will be approximately towards the right hand side of 5.5 maybe. So this is a bit above 500. That's 600 amount, so 530 maybe somewhere here, maybe a little bit higher there. Okay, so then you go back down to the value of the field current. Okay, maybe somewhere here. So IF comes to 5.7 amperes. Let's say you're doing this kind of question in the exam, so if you're not able to read the exact value, you read it as 5.6, 5.8, that is acceptable. Okay, so we're looking at solving the question, so make sure that you read through the statement carefully. Spend some time. The first part of the question is looking for the speed of rotation of this generator. So the speed at which generator is rotating is Nm, and it's the speed at which the rotating magnetic field is also rotating. So 120, the electrical supply frequency divided by number of poles. So if you look carefully through the statement, the machine has the 4 number of poles. And what is the frequency? The frequency it is running or producing the supply, the electrical supply, at is 60 hertz. So substituting everything together, it gives you the speed of rotation of the generator 1800 RPM. So that's the first part of the question is very simple, and that's it. The second part of the question we're looking at if the generator is connected to a load that draws 1200 amperes at 0.8 power factor lagging, so it's a lagging power factor. How much field current is required to help the terminal voltage equals to 480. So we have to first look at a situation. What is the internal voltage required in order to have the terminal voltage of 480? And once we have that, then we're going to go back to the graph posted on the previous page to see what is the field current required in order to generate, in order to induce an internal voltage of that amount. So looks like we need to use the equation which relates EA and V phase for a lagging power factor load. So for the lagging power factor load, so this is part 2, the equation is EA equals to V phase plus IA RA plus any drop across the synchronous reactance. And what kind of connection is this? Is this a delta connection or this is a Y connection? We have to look for that as well. So this is a delta connected system. In case of a delta connected system, I phase and I line are different, so we have to be careful for that. In case of delta connected system, so let's say IA, I'm saying is the phase current, that's going to be, it says it's at 1200 amperes is the current it withdraws, which is the line current. So IA is going to be 1200 divided by root 3. This might not be required in case of Y connection, so make sure we carefully apply the type of the connection. So that's the amount of the current, the amplitude, but since we're using the complex numbers here, it's using I, so I has 90 degrees, so the current has to use its angle as well. So it's a 0.8 power factor lagging. First of all, the angle is going to be negative. Based off of that, here is your V phase, and here is your IA in this case. So IA will have an angle negative, and this angle negative you will be based off of that the power factor is 0.8, so theta will be cos inverse of 0.8, and the calculation gives you an angle of 36.87 degrees. So that's the complete value of IA which we will use. I believe rest of the components are known to us, so let's substitute and see. And yeah, one more thing, V phase, we're required to have V phase of 480 volts. Okay, so what else is there? You have the synchronous reactance of 0.1 and the resistance value, we need to also look for it. Okay, so internal resistance of the armature is 0.015 and the reactance is 0.1. So let's substitute everything together. EA equals to sorry, V phase, which is 480 to an angle of 0, plus IA, which we calculated 692.8 to an angle of negative 36.87, multiply RA, which is 0.015, plus the next term is I times again is the current, exact same value, and the amount of the reactance is 0.1. So use your calculator to solve for this, and what we got for EA is 529 decimal 9 plus the imaginary part is 49.2, and we need to change this to polar form. You can definitely use your calculators to do all these calculations in volts. So that's EA. So in order to keep the terminal voltage at 480 volts, the internally generated voltage must be 532. Now let's go to the graph between EA and IF. I think it's posted on page 11 somewhere, and see what is the amount of the field current which is required to produce EA of 532. So here we're gonna say IF is 5.7 amperes. Next part of the question is asking how much power is the generator now supplying. How much power is supplied to the generator by the prime mover? What is the overall efficiency of the machine? So part C, it's looking for what power is supplied by the generator. So we're looking for P out. So the P out is given by 3 V phase IA cos theta. Let's substitute all the values. 3 V phase is 480, and for this condition the current was calculated 692.8, and it's running at a power factor of 0.8. So that gives you 798 in kilowatts. And so this is the power generator is producing. Then it says how much power is supplied to the generator by the prime mover. So it's also looking for the input power supplied by the prime mover to the generator. And we're aware that P input is given by P output plus losses. And in this case, let's see what are the amount of the losses. So P input equals to the output value calculated 798 kilowatts plus any losses. So the types of losses here, one type of loss is in the armature winding resistance. Since it's a 3-phase, so we're going to make sure it's I square R, which is IA square times RA, and this 3 factor is to include the 3 phases. And we're also given an amount of the losses here as the friction and the windage as 40, so we're going to use that as it is. 40 plus the core losses as 30 kilowatts in the question, so we're going to use those numbers as it is. Here this is kilowatts, that's kilowatts, that's kilowatts. In order to change this amount to kilowatts, we will divide it by 1,000 in the calculation so that all numbers are of the same level of the units. So 798 plus, here this will be 692.8 square multiplied by RA, which was 0.015, divided by 1,000 in order to change it to kilowatts, plus 30 plus 40, 70 kilowatts, and the amount of the input power comes as 889.6 kilowatts again, and the efficiency will be calculated as the ratio of the output power to input power, and in percent, of course, multiplied by 102. So output power was 798 divided by 889 multiplied by 100, so that gives you an efficiency of the amount of 89.75%. That was part C. Okay, part D of the question is, if the generator's load were suddenly disconnected from the line, what would happen to its terminal voltage? So we're looking at any change in V phase if load got disconnected. Now with the load disconnection, we're aware that IA is going to be 0, and in that case EA will go equals to V phase. Now what value of EA? That's the question now. So V phase equals to EA. In the previous step, we calculated the value of EA for terminal voltage of 480 as 532. Since there's no change in the field current, so the EA, the induced voltage, depends on the field, the magnetic field in the rotor. So that's why EA will remain 532 volts. And now under no load condition, your terminal voltage will become equals to 532. So that was part D of the question. Now the last part is the part E, and please read carefully. So suppose that the generator is connected to a load drawing 1200 amperes at 0.8 power factor leading. How much field current would be required to keep the VT at 480 volts? And now what we have done is we have changed the load situation to leading power factor. So in this case we have V phase here, and IA will be here at the same power factor of 0.8. So theta is leading now. So IA will change to IA 692.8, which was its value, because value is still at 1200 as the line current, so phase remains the same. The angle will now change to positive 36.87 in degrees. So we'll calculate the value of EA using the same equation, V phase plus IARA plus IAXS. So I'll write down the equation one more time. So it was V phase plus IARA plus IAXS. So V phase is required to remain same plus the drop across the resistance. Sorry, I forgot again the angle for the current. So angle 36.87. That's drop across the resistance. Again, you can use calculator to do the calculation. So EA comes as 451 to an angle of 7.1 degrees in volts. So now the value of EA is here. So go to the graph between EA and IF on page previously, somewhere page 11, and calculate the value of IF, and the value of IF is coming as 4.1 amperes. Okay, so thank you very much.